Well, looks like we can start. Welcome back and happy almost weekend. After today's class is over, we're going to be 75% done with the entire semester. And the standard announcement is next Monday, we'll be having the official day for our exam 3. So we won't have class on that day. Just in case people do schedule their exam right on that day, there won't be any overlap, anything like that. Also gives us a bit of a breathing room, a little bit of a pause in the course before we get into the next sections. So if you haven't done so, please schedule your third exam. Otherwise, we're all set. It's going to go down just pretty much how exam 1, exam 2 went. Entirely the same. And aside from that, we're actually most of the way done with the section 5.2 notes. We're currently on example 4, looking into when a definite integral, this kind of object, will not exist, when the limit of the Riemann sum fails to give us a finite actual area. But that's where we're at the moment. I guess I don't have a whole lot of announcements to start us out today, but any questions to start? Okay, well, here's where we left off last time. On example 4, with theorem 3 cited nearby, just because it's a nice theorem to help us out through this one, we're looking at the expression integrate from 0 to pi tangent x dx. We're wondering if the integral exists, which boils down to, does the limit of Riemann sums exist? But if it's a direct question about the integral, we don't have to write this in the form of the limit. We'll only do that if the instructions explicitly ask us to do so. Theorem 3 tells us that if a function's continuous on a closed interval, or if it has a finite number of jump discontinuities, then we can measure the area under the curve. In other words, that function f will be integrable on the closed domain from a to b. The integral of f of x will exist, in other words. So all we're doing this time is switching the f of x to a particular integrand. The integrand is now tangent x. So to wonder if the integral exists, it really just boils down to determine if the interval is continuous on the closed interval from a to b, which in our problem goes from 0 to pi. And tangent x is continuous on its domain, but we have to be very careful when we say on its domain. Let's take a really close look at the tangent x function. If f of x is tangent x, then we know the definition of that function is the ratio of the sine over cosine functions. If we're on a domain from 0 to pi, there's one problem right at pi over 2, the center of that domain. This tells us that f at pi over 2, which is sine pi over 2, no problem there, that's exactly 1, divided by cosine pi over 2, that's a division by 0. Really using inequalities here is kind of meaningless. Whether you're on this side, sine pi over 2 divided by cosine pi over 2, or on the right-hand side, 1 divided by 0, it's undefined. Now we have to ask the question of, why is it undefined? We know we have a discontinuity there. A discontinuity will always occur when the function's undefined. But this discontinuity is actually particularly bad. When we had 0 in the denominator, it's undefined because there is a vertical asymptote. In other words, tangent x has an infinite discontinuity at x equals pi over 2. A big vertical asymptote. Let's take a look at the graph because seeing is believing. Here's tangent x. We're on a domain 0 from less than or equals to x, less than or equals to pi. And we can absolutely see there's a vertical asymptote right there. The curve shoots up vertically in one direction. If you approach from the other direction, the right-hand side, it shoots down, heading towards negative infinity. We don't have any sense for the area of this particular function. the area doesn't exist. We have an infinite discontinuity, and the theorem was forgiving with discontinuities only if they were jump discontinuities. So this one is a no-go for us. So here we can say the integral from 0 to pi tangent x dx does not exist. There's no notion for the bounded area under the graph of this particular function. So anytime we go to integrate a function, these are the things we have to watch out for. And it gets a little bit worse in calculus 2 when we look into improper integrals. We always have to ask ourselves and answer, are there continuity issues? Because this theorem only guarantees integrability if we know we have a continuous function. Well, that's the quick tour of what can go wrong when we write down a definite integral like this one. Any questions on example 4 before we look into properties of the integral? Okay, well, much like properties of the limit from chapter 2, properties of the derivative throughout chapter 3, there's plenty of properties for the integral. Calculus 1 gets through a lot of them, and calculus 2 is going to pick up right in chapter 7 where we leave off, looking into either even more properties of the integral, different ways to integrate. But here's what we have so far. Properties of the definite integral, 1 through 6, give us a curious set of properties. One of them that's kind of interesting is if you integrate from a b to an a and swap it from a to b, you get a negative sign in front of the integral. So if you change the order of the limits of integration, you would always get a negative sign. Another one says, if you say integrate from a to a of a function f of x dx, that integral is always automatically 0. One way to think about this one is, this is measuring the area under a curve, so you need an actual width to measure that area. But if that width shrinks down to just a line, A, the area of a vertical line segment is just 0 itself. We have a constant multiple rule, or excuse me, just a constant rule is a better way to say this one. The integral of a constant from A to B is just a constant times B minus A. One way to look at that one is, if it wasn't a tangent function and it was just, say, y equals 1, well, if you integrate y equals 1 and you're going from 0 to pi, it's just the area under the curve from 0 to pi. We can calculate that area. You just take the length. Going from here, the length is pi. That'd be pi minus 0 times the height, which is the constant 1. And that's all this is doing, measuring the length of the interval, multiplying it by the height, the number that constant happened to be. So that's what the constant rule is telling us altogether. Property 4 says we can break up integrals across a sum. So whether it's pluses or minuses, multiple terms, more than 2, there's a finite number of terms, we can integrate term by term, which is similar to how we so often differentiate term by term. And they keep going, but any questions with the properties so far, 1 through 4? Okay, property 5 is the constant multiple rule for integration. Same kind of rule we had for differentiation. It says if you're finding the area under a curve, f of x, but you multiply that curve by, say, 2, that just moves the curve up by a factor of 2. So the area under the curve, which is this part highlighted, should be that factor multiplied. So you can move the constant, the short of it, outside of the integral, as long as it's a true constant with respect to the variable of integration, dx. So that's our constant multiple rule. That can sometimes be really helpful for us. And this one's kind of curious. It's a way of partitioning an interval. This says if you're finding the area as you go from, say, A to C, actually, let me just highlight this one. If you find the area as you go from A to C, and then find the area as you go from C to B, Really, that should just be the area as you go from A to B. It's the area of one segment plus the area of another segment, and you can put the integrals together, just the area from A to B in total. So that's our short list of properties of the indefinite integral so far. A lot of these are intuitive properties, say this property right here. Many properties come just from the form of the Riemann sum definition. If you swap this around, your delta x is no longer a minus b here. It would become negative b minus a minus b, or b minus a. Factor out a negative sign and you change the order of integration. So that one's through the definition of the Riemann sum. And this one's just a consequence of properties of limits themselves. What we'll do is a few problems just practicing with these properties. But any questions with them as we have them so far? Okay, well, this is kind of an exciting moment because now we're going to do our very first integrals without using any limits of Riemann sums. We want to integrate the linear function 5x plus 1. And we're going to find out a lot of great ways to do that in the next section. But if all we have so far for integration, and we don't want to do the limit of Riemann sums, then we're going to want to use these properties 1 through 6 in a clever way to get us that area. So let's rewrite this. Integral from 0 to 2, 5x plus 1. One thing we can do is just break this up. There's two functions here, the 5x function, the constant function 1. So using property number 4, we can rewrite this as integrate from 0 to 2, the function 5x, plus integrate from 0 to 2, the function 1. So here's the 5x function playing the role of f, coming off on the right-hand side. And here's the g of x function, just a constant function, identically equal to 1, coming off to the right, just like in the property above. So now we need to integrate, well, twice as many things, but this is slightly easier to get through. One thing we can do is just go to the geometric intuitive idea of what an integral is. The definite integral 5x is the area under the curve from 0 to 2 of the 5x function. Because it's linear, it's not so bad to find that area. We're going to go from 0 to 2. My scales are going to have different widths. This is 0 to 2 on the horizontal axis, up to 10 that far on the vertical axis. The y-intercept of the 5x function is at the origin, and when you plug in 2, you would get 10. So here's y equals 5x. We can absolutely find the area under this curve pretty quickly. It's just a triangle. If it was, say, x cubed, that'd be a little bit more challenging. But we can just say that this area, all right, just A for area, is 1/2. The base times the height. The length of the base is going this way, just 2. So this is 1/2 times 2. Times the length of the height is going this way, and that's a value of 10. So it's 10 altogether. And that's what this entire integral is going to come out as. It's just overall 10, nothing else. You still have to do this integral, and we can draw another figure. It's really property number 3, but drawing another diagram doesn't hurt either. For integrating from, say, 0 to 2, here's a new graph. Let me see if I can fix that, those tick marks there. Okay, so this time the scale looks a little bit more 1-to-1. The function is constant, always equal to 1, so its graph would look like this. At input 0, its height is 1. At input 2, its height is 1. So there it is, y equals 1, just a line segment. Getting the area under that curve even faster than the first function because it's just a quick rectangle. We can say the area of this one is equal to the base times the height. Base is length 2. The height is 1. So we will get just area 2 altogether. If you use property 3 here, you just put in a 1 for the constant. b minus a would be 2 minus 0, and it's going to be 1 times 2. Either way you look at it, the area is coming out as 2. So putting these together, the area under the curve from 0 to 2 of 5x came out as a 10. The integral from 0 to 2 of the function 1 came out as a 2. And so the total area under the curve identically equal to 12. We could have plotted the whole function 5x plus 1 and used area arguments on that one, but we broke it up because I think it is actually slightly easier to break it up, but also allowed us to use property number 4 to see how it goes. Well, that's one integral so far. We'll do many more before the course is over, and 2 more to go in these notes. Any questions with example number 5? Okay, example 6 looks funny. It almost looks like a typo sometimes when you see these for the first time, but it's not a typo. That's a valid integral to write down. These things sometimes occur in calculus, where the lower bound is the bigger number than the upper bound of integration, which is 0. It's really pretty weird, but you can find the integral of that. So if we integrate from 2 to 0, a 5x plus 1, to make sense of this, probably the best thing we can do is use property number 1 that says if you swap the limits of integration, all you have to do is multiply by -1. So if this makes you uncomfortable, we can fix it, and it's a good idea. It's fixable by putting in a negative, integrate from 0 to 2 of the same integrand, 5x plus 1. And that's where that negative sign comes from in property number 1. We're essentially done right at this step. Once we fix this and we're integrating from 0 to 2, we're just taking -1 times the answer from part A. So this becomes -12 altogether, and our work is done by reusing part A. So in a certain sense, what's going on with this one is integration has a certain direction we like to read things off. If you're going backwards from an upper value to a lower value, we consider our area to be negative in that sense. So we get to -12 altogether. Going in the normal direction for a positive function, going from left to right, our area would come out positive, like in this case here. So that was the good use of property number 1. And property number 1 is one of those things where it seems like a weird parlor trick, but even in this course and later on courses, it's kind of amazing how this one just sometimes simplifies problems. It becomes a necessary trick, depending on just what you're doing, what you're about to integrate. So last one is example number 7. And nothing too severe. We're still dealing with the 5x plus 1, but we're multiplying the whole thing by 100. And you can work really hard on this one. Distribute 100 in. Now you have 500x plus 100. You can use area arguments to find the area under that linear function. Or you could break it up like this, where it's a 500x, 100, 2 more diagrams, get those areas and put them all together. That works fine too. But the best way to handle this one is, what it's really all about is the constant multiple rule. If you have a constant times f of x, if that's your integrand, then a constant can move outside the integral, and you can just integrate f of x, multiply the result by that constant. This is something that's used quite a lot in calculus whenever we're dealing with the integral, because sometimes if you can simplify what's inside the integrand as much as possible, eliminating constants even, it's well worth the effort to try to find a way to solve the problem. So that's a pretty commonly used property. There's our constant here, playing the role of 100. So it tells us if we integrate from 0 to 2 of 100 times 5x plus 1, we don't have to work so hard. We already know the integral of 5x plus 1. So put 100 in front by the constant multiple rule. Let's highlight these to show how they moved by property number 5. And at this stage, we're essentially done. We just take 100 times the known value for the integral of 5x plus 1 from part A, or example 5 right here. We got 12, so it's 100 times 12 for 1200 is now the total area under this curve, 100 times 5x plus 1. So that's a pretty fast tour through the properties of integrals. Any questions getting through any one of those examples at the moment? Okay, well, we have one more example to take a look into before we find out how to integrate these things in a more efficient kind of way using the fundamental theorem of calculus part 2. Before we do part 2, we need to deal with part 1, which is a pretty bizarre function that we're working on in the fundamental theorem part 1. Here's the properties of the definite integral again. I'm not sure why I copied it here. I don't think we're using M2 directly, but we're really focusing on that function here. It's a pretty bizarre looking function. F of x, capital F of x, because it's weird, is defined to be a definite integral from 0 up to x. So that's the input, the independent variable. X is what's varying. It's telling us that we're integrating up to a value x. We're finding the area up to x under the curve f of t dt. We could have called it f of x dx, but it feels like a conflict of notation if you have the integrand use the same variable as the upper limit of integration. So we resolve this by just changing out from what might have been an x to any other variable. That variable could be u, v, a smiley face. We chose t on this example here. This is in fact a pretty common function. It's possible you've worked with these functions before in probability using normal distributions, the normal curve. This is referred to as an integral function. And our author likes to call it the area so far function. The area so far as you go up to x. So f is the function that's plotted in the graph below. Uppercase f of x is going to find the area up to a value x. So wherever x is, we just find the area up to that point. We want to know, if that's the case for this interesting function that's defined, which of the following values is the largest. And I think that instructions ask for another question. Let's add just a little bit more. Sorry for the quick edit here. Which of the following values is the largest? And which is the smallest? I think that would be more interesting with that quick change there. Let's also move that arrow around. Okay, so to solve a problem like this one, we just have to think in terms of what is the concept of the integration. We're just finding the area under the curve. And as far as f of 0 goes, maybe this is what I was thinking of with the properties up above. We'll look at them briefly. F of 0 is an interesting property because if you swap x to a value 0 right here, it means you're integrating from 0 to 0 f of t dt. Or if you're looking at this more graphically, geometrically, it means the area under the curve that's blue as you go from 0 to 0. That's just the area of a vertical line segment. The area's got to be 0. That's also what property number 2 is saying. The area from A to A, if your lower limit and upper limit are both identical, exactly the same, this is always identically equal to 0 each and every time. So f of 0 is equal to 0 on this function. And now we're going to take a look into how to compare all the rest of them. But that's one down. That's a good start. 5 more to go. If we do f at 1, well, f at 1 would be this area. So here's f at 1 with just some temporary highlighting so the graph doesn't get too busy. What I can tell you about f at 1 is I don't know its exact value. But it's absolutely true that f at 1 is positive. So we've got that for sure. Likewise, if we look at f of 2 is going to be integrate from 0 up to 2. That's finding the area of the curve under the curve here in blue from 0 up to 2. And that would be this area. That absolutely exceeds f at 1 because the area stopped at this boundary value, the vertical line segment x equals 1. So we also have that f at 2 is positive, and f at 1 is smaller than f at 2. So we're painting a picture of this so far. We have a value of f at 2, and now we wonder what happens when we put in f at 3. If we can estimate these values, we'll get an idea of which value is the largest and which value is the smallest. So let's reset our highlighting. And let me put in another pen. I guess that's a pencil. Let's put in another pencil. So the one in orange, that's going to be positive. The one in purple, that's going to be negative. And if we're doing f at 3, let's write this out just for reference sake. That means integrate from 0 to 3, f at t dt. We say that this is a definite integral. It's the area under the curve f at t. But the full story, like we discussed at the very top of these notes, is it's really a net area. Some of these areas are signed. They're positive when the curve is above the x-axis. So this would be positive area, integrating from 0 up to 2. But we keep integrating up to 3. And when the curve is below the x-axis, that area is now negative. So f at 3, it's still a positive value because there's more positive area visually than there is negative area. So we can say f at 3 is certainly bigger than 0. What else can we say about it? Well, it's not as big as f at 2, because f at 2 is just this area. We didn't subtract off the negative area. Visually, it looks like it might be about as close as f at 1. We have the f at 3 is approximately equal to f at 1. I don't know if that's exact or not, just visually looking at it. This purple wedge here looks like it'd be at about the same area as this wedge here where the red dot is. So it's a positive value, but f at 2 looks like it's still the largest value that we're going to come up with. That might be the absolute maximum of this function. Then we keep on going further, but any questions with these values from f of 0 up to f at 3? Okay, let's push it further. Now we're looking at f at 4. When we go from f at 4, we pick up all of this positive area, but then we keep on integrating. That positive area, when it balances together, is getting smaller and smaller until it stops about here. So all of that is the negative area. It's going to add together with the positive area. And this looks pretty symmetrical to me. That looks like it would balance to pretty close to 0, if not exact 0. I just can't say it exact because it's a visual estimate. But it looks like f at 4 is approximately 0, if not dead on 0. So f at 1 is positive. F at 2 is also positive, but it was larger. F at 3 is close to f at 1, so f at 2 is still winning. And f at 4 is pretty close to 0. So at the moment, f at 4 looks like it's the smallest value. But then we push it even farther. If we go to f at 5, that means we are integrating beyond the point where the symmetry seems to occur. This point seems to match up with that point in the symmetry. But then we go beyond further. We integrate when the curve comes back up to the horizontal axis. And now this area, it looks bigger than this area. There's more area that's considered negative below the x-axis than area that's considered positive. And that would mean for f at 5 is absolutely negative. It's the only one where we can say it's definitely a negative area altogether. So f at 5 is going to be smaller than f at 4. It's smaller than everything else, which was positive. And now we can say which is the smallest, which is the largest. So let's say altogether, f at 5 is the absolute minimum. F at 2 is the absolute maximum. And there's a problem just about like this in the homework as well. This is kind of the way to think about it. Imagining the area being swept out as the values change from one to the next. And in doing that, making some reportings of how things landed, f at 3, f at 1 being close, f at 4 being about 0, and so on, we can get a good idea of what the highest value should be and the minimum value should be for an integral function like this one. So that's our introduction to a weird class of functions. We've never seen one quite like this. Not as weird as defining a trig function like sine and cosine, in my opinion. That one is a little bit weirder. But this one's an area function in a certain sense. Like any other kind of function, you could plot uppercase f of x. And you know what? It's also continuous. It's also differentiable. We can differentiate that function. And that's what the fundamental theorem of calculus part 1 is really all about. So this is kind of a segue problem now to section 5.3. But any questions or thoughts before we go to that next section, the fundamental theorems of calculus? Okay, well, let's crack open those next set of notes and take a look at what's going on. It certainly has a fancy title. Whenever you're delving into a new subject, there is typically always a fundamental theorem. For example, there's a fundamental theorem of arithmetic. It tells us that any number you write down is either a prime or can be decomposed uniquely into a product of primes. There's a fundamental theorem of algebra, which says if we write down a polynomial of degree n, there's going to be at most n roots. And now there's a fundamental theorem of calculus. This one is split into two parts. There is the differentiation theorem, and the next is going to be the evaluation theorem. So we're going to first, in the fundamental theorem of part 1, start with the continuous function f on a closed interval from a to b, and define an integral function, just like on the very last example, g. G is defined to be an integral from a to x of f of t dt. A came from the lower bound of that domain here, and x is the input variable. So that's why x cannot exceed b, because that's how far the function gets defined. It's constrained between a and b. So very similar to the last problem we were taking a look at. That very last problem is just a typical example of an integral function like this one. So here's what the fundamental theorem part 1 says about these kinds of functions. This function g is also continuous on the closed interval from a to b. It's differentiable on the open interval from a to b. And the derivative of that function, here's the crazy part, is the integrand f of x. We swap from the variable t, which is so we don't have a conflict of notation with that variable x, and we go back to x here. So that's a really bold statement. One question you might have is, how do you prove something like that? The book does a great job. If you skim through the proof, no harm done really, but it's not a bad idea to take a look into it. What they have to do to prove this is use the definition of the derivative on that function right there, and then we use the extreme value theorem for a function that's continuous on a to b. This was from section 4.1. We abused it for the closed interval method. And what it told us is if a function's continuous on a closed interval, it has an absolute maximum and an absolute minimum. So using those facts, along with the definition of the derivative, you can crank out the derivative of g, and a weird thing happens. You get f of x. It's the strangest thing in the world. It becomes one of the weirdest looking derivatives ever, but it's also one of the faster derivatives. So that's the good thing about it. So whatever your integrand happened to be, the derivative of g is f of x. Just recall, you have to swap to variable x when you state your answer. We write all of this out in Leibniz notation. It's the same information, but it almost feels like it tells a different story. This is saying the derivative with respect to x of the integral from a to x of f of t dt is just f of x. It's as if those signs canceled, and of course we swapped from t to x. And it's in that kind of sense that we can think of differentiation, d by dx, that's just finding the slope of the tangent line, is an inverse process to the operation of integrating from a to x of some continuous function. They are opposite to each other in this weird kind of way. So the derivative is just the integrand. Again, a really bizarre property. This is an important property in its own right. For example, probability, using normal distributions, the normal curve, deals with these functions to come up with proper probabilities. So finding the derivative of those kinds of things is a natural process. But also, this is going to lead into the bigger topic, the one that we're all here for, how to do a definite integral without resorting to the limit definition. Before we get there, we'll practice a little bit with the fundamental theorem, part 1. Any questions or comments about this so far? Okay, maybe a couple more words about the fundamental theorem, part 1. This is one of those theorems that it really just doesn't get enough of its credit it's really owed. It's a pretty important theorem. It's one of those theorems that's easy to forget when you get deep into calculus 2 until it shows up randomly. Maybe you're taking a differential equations class, and all of a sudden, fundamental theorem calculus part 1 comes up, and you're left scratching your head. What was that all about? Why are we doing this? And here's one of the weird issues, and the reason this is actually a very powerful theorem. Let's write down a really complicated function, y equals e to the power of x cubed. I'll put parentheses there to show the order of these function compositions. This function is continuous. It automatically will have an antiderivative, just knowing that information. But finding antiderivatives is a weird process. We hinted at that a little bit before, and it turns out, sure, you can write down any function, and with the right series of steps from chapter 3, product rule, chain rule, quotient rule, so on, we can always get the derivative of that function if it's differentiable. But it's possible to write down a function like this, which is continuous, and all of our methods are going to fail in finding the antiderivative. The words we use here is that this has no closed form antiderivative. So an absolutely unfair question to put in section 4.9 on antiderivatives. What we mean by closed form is I cannot write a formula for this antiderivative without using an integral sign, that's cheating, or without using infinitely many terms of algebraic structures added together, which would be called, say, a power series. So it doesn't have a way to write a formula for its antiderivative, yet the antiderivative exists. If we need to write down something for the antiderivative that goes beyond a closed form, just because maybe we're doing something in calculus 2, something in differential equations, we can still do it. And that's what the fundamental theorem of calculus part 1 gives us. We can say if f of x equals an integral from any constant, I'll put in a constant 0, just as a generic one, to x of e to the power, I don't want to say x again, it's a conflict of notation with the dx, so I'll say t cubed dt, then f is an antiderivative because f prime at x is equal to e to the x cubed, which is the application of the fundamental theorem of calculus, part one, visualized in Newton's prime notation. So this is one of the major uses of it. For our course, we're just going to practice using it a little bit. But if you're doing a lot more work in calculus, differential equations, engineering mathematics, this is something that just keeps on coming back. So with that kind of preamble out of the way with how to use it, what its good uses are for, we'll differentiate a few functions, just seeing how this goes. And again, I think you'll like it. Once you are familiar with this process and you know how it goes, this is the whole story for this derivative. If g of x is the area under the curve from 0 to x of the square root t squared plus 4 dt, finding an antiderivative of that is pretty tough, but you can just say, if the goal is to find the derivative of the function, g prime at x, is automatically done. It's the square root of x squared plus 4, and there is nothing further to that story. All you had to do is grab the integrand, swap to variable x, and the job is done right at that moment. It makes it kind of an awkward question on a final exam because it feels like we should do more. So watch out for these. When this comes up, that's all you ever had to do for the problem. Any questions or comments getting through part A? Okay, part B is a little bit awkward because notice where x occurs on this one. That's actually not good. When we use the fundamental theorem of calculus part one, the position of x is actually important. It's got to be the upper limit of integration. So the moment you see that x is the lower limit of integration, that's something that has to be fixed right away before we differentiate. But that's not so bad. We can go to the properties of the definite integral. It says you can swap the limits of integration, just throw a negative sign in front. So first thing we do on this one is we say g of x is equal to negative integrate from 0 to x. That's where we want to see x, up in the upper limit of integration, hyperbolic sign of e to the t, dt, there's our integrand. And now right at this stage, we're ready to differentiate. All we had to worry about was where the upper limit of integration was. So that's the new thing on this problem. G prime at x is then, through the constant multiple rule, this is -1 times a function, so that negative carries in. The derivative of this, through the fundamental theorem part one, is just hyperbolic sign of e to the variable is x. So we swap to x. That's an easy mistake to make. And it is important for full credit. If we say g of x or g prime at x, the answer has to be in the variable x as well. But that's it. Once we corrected the upper limit of integration, the derivative is automatic. The integrand is the answer to the derivative of the function. So we'll try out one more and then look at part two, the evaluation theorem. So here's the next one to take a look into. Part C has x where we want it, so that's nice. Let me scroll up just a little bit. It's right up here in the upper limit of integration. But there's more going on with x. As an input, it's not just x any longer. If it's x cubed, this one becomes a true chain rule problem. So because of the x power 3 there, we're going to use chain rule. That's the function 2. Inner. In place of where we expect x, like in the last problem, if you throw anything else in there, now it's a chain rule problem. So that's function 2, inner, function 1, outer. In the chain rule process, I'll just point to the integral sign, is the integral function itself. And this one is a chain rule problem. But as far as the chain rule goes, it's always going to be the same kind of story. Let's highlight this in blue. That's the integrand. And when we go to calculate z prime at x, we take the derivative of the outer function, the integral function itself. Well, the derivative of that is going to be the integrand, but in place of where we would have put the x, we're going to put a placeholder. It would have been x natural log x. So we'll say placeholder times natural log placeholder. Then we chain on a new derivative, the derivative of whatever the inner function happened to be. That inner function is x cubed. So, I kind of wish I color coded that differently. Let me write this in this way. Okay, so the part in blue is the derivative of the integral function, the outer. The part in green is the inner function. We had two places where we would have put x in. So those are places we put in x cubed through the chain rule. And now that's our derivative to take. Really, the last thing to do is differentiate x cubed. That's just going to be a 3x squared. So this becomes x cubed, natural log x cubed, times 3x squared. Then we can simplify a little bit further, combine like bases. This is 3x power 5, natural log x cubed. That's a good stopping point. If you feel like being fancy, you can move that 3 as an exponent out in front as a coefficient. You're just practicing properties of logarithms, which we should always refresh. That comes out as a 9x power 5 natural log x. But if you stopped at the red dot, that's a fine stopping point too. So that's about as crazy as these can get. I'm not going to combine these things with product rule, quotient rule. I think that gets a little bit excessive. But a chain rule is still kind of appropriate to visualize how it would work for an integral function like these. Well, that's the fundamental theorem, part 1 in a nutshell. There's a lot more to the story of how useful it can be, but that's going to be further content in Calculus 2 and differential equations. But any last questions at all before we change gears to the next topic? Okay, well, here is finally the fundamental theorem of calculus, part 2. And a lot of times when people say fundamental theorem of calculus, if they don't say which part, they probably mean this part right here. It starts off kind of same as before. Continuity has a really huge role to play in calculus. So if we're continuous, we'll know the definite integral exists per the last section. Continuous particularly on a closed interval, and we're integrating on that integral from a to b. And here's where antiderivatives finally play a really critical role. This thing is a complicated limit. Let's pull up that limit just for a reference. It's in a lot of spots, but I think this will do the job. It's a limit of this form where xi is a sample point in an ith interval where we partition a domain from a to b in n subintervals. So that's the thing that we're taking as a limit. It's a oftentimes very complicated limit to compute, but the fundamental theorem of calculus part 2, discovered by Isaac Newton and Leibniz, says the definite integral from a to b, which is just a signed area, is the antiderivative of f minus the antiderivative of a. That is a remarkable fact, that the area under a curve, which is a complicated process through a very, very complicated looking limit to Riemann sums, boils down to just the antiderivative on 2 points. No matter how complicated the curve gets in the middle of this domain, it's irrelevant. The moment you have the antiderivative, you have the exact area under the curve that this limit would converge to if it exists. And it will exist as long as you're continuous on a closed interval. The way this one gets proved is it takes some clever arguments, but this is where the mean value theorem gets used to prove the fundamental theorem of calculus part 2. So just a reminder, when we say antiderivative, let's use the same color coding in section 4.9. If that's our function, the antiderivative f of a just satisfies the property f prime is lowercase f. So suddenly, finding an antiderivative becomes a critical process because that's what's going to allow us to integrate a function like this in a definite integral. If we express this in Leibniz notation, looks a little bit awkward, but this is all it's saying. It's the same information. Here's the function. This is the antiderivative, because if you differentiate f, you get to that, the thing that's the integrand here in green. So Leibniz notation is conveying the same information, just using d over dx. I did make a revision on these notes. I felt like coming back to cosine was a good idea for us, because this is a problem that we estimated in section 5.1 when we were just thinking about area under the curve. So now we're going to do this exactly through the fundamental theorem, part 2. Any questions before we get started? Okay, well, this is the way the fundamental theorem gets stated in either Newton's notation or Leibniz notation. But there is one critical piece of notation. In fact, let's say that. Critical notation is actually used when you go to read examples in the textbook, or you're maybe taking another calculus class, maybe calculus 2, from whoever you're taking it. They're probably going to use this notation as well. When people say f of b minus f of a, and they're solving a problem like this one, it's actually written a little bit differently. We find the antiderivative of the function, and we write f of x, the antiderivative. We put down an evaluation bar. Some people put brackets like that. Some people put bars just like that. And we've seen these before when we write out stuff like dx, let's say it this way, dy dx. Evaluate at x equals a number like 5. We put in those evaluation bars before, dealing with Leibniz notation. Here what we'll say is it's going to be an evaluation bar as we go from a to b. And we always take that kind of evaluation to mean f at b minus f of a. I'm calling it critical notation because this is notation I encourage you to use as well, because it's used essentially everywhere in the textbook, as well as when people integrate. This is a notational device that's almost always used as an intermediate step. So we'll use this as well as we go through the notes. And here's how the process is going to start. Evaluate the integral is all it says. First thing we need to do is find the antiderivative for cosine x. So here's the integrand, cosine x. The antiderivative of this would be sine x. That's because if we put sine x here, differentiate it, you'll get the integrand cosine x, exactly, not even off by a sign. So once we find the value, sine x, the next thing you would see in the steps, reading the textbook, for example, is the evaluation bar, which says to evaluate from 0 to pi over 2. Again, that notation is used so much that it's a good idea to internalize it. It's a decent shorthand as well. I encourage you to get in the habit of using it in your own work. Once we have that, the theorem says, take your antiderivative, evaluate it at the upper limit of integration. For us, that's pi over 2. So we'll go sine pi over 2. Then go minus. Take the same antiderivative, evaluate it at the lower limit of integration, which is 0. Go minus sine 0. And you just have to simplify whatever you've got. Sine pi over 2 is 1. Sine 0 is 0. And so that's the whole story to this one. It's telling us that the dead on exact, not an estimate, not budging even by a little infinitesimal amount, exact area under the curve of cosine on the domain from 0 to pi over 2 is 1 exactly. Kind of strange, remarkable fact. And we got decently close to that fact as well. When we did this, say, all the way back in section 5.1, here's what it looked like. We were finding the area under the curve, f of x is cosine x, and we even color coded it the same. That's an accident, a nice accident. We partitioned the number line from 0 to pi over 2 using 4 subintervals, and we did this with the left endpoint rule. It's tedious. It took a lot of work because we had to find the height of the rectangle, the width was pi over 8, evaluate cosine at all those values, and we got all this stuff out. We knew it was approximation, and it came out to 1.183. We even said it's an overestimate. And we can see the overestimate visually. If we used n as 40, it wouldn't have been as bad. It would have been closer, but it still would have been above 1. If we take the limit as n goes to infinity, it would have converged to exactly 1. But the limit of these kinds of terms is really, really complicated to resolve. And so that's the sheer power of the fundamental theorem part 2. A really great theorem in mathematics takes something that's monstrously complicated. And trust me, these limits are very, very complicated to compute, whether it's the right endpoint rule, left endpoint rule, and so on. A great theorem takes things that are monstrously difficult and shows you a streamlined process to do the computation. We didn't even have to write down a limit, but we have the exact area under the cosine curve now. And then the whole problem is over right at that step. So a definite integral gives you a number, which is the net area. And we'll try it again for this function. From 0 to 2 of 5x plus 1. Any questions at all with part A first? Okay, well, this is the one that we did in just today's notes. We use the properties of integrals to break it into 2 terms. We don't actually have to do that at all. We can just find the antiderivative of 5x plus 1 as a function, just the way it sits right here. There's no need to actually break up the integral into 2 different integrals. Also, when we did this, we were using algebraic arguments, geometry, and we got an area of 12. Those kind of arguments fall flat on their face if this was x cubed. We wouldn't have a triangle to use the area of a triangle any longer. So now this one, we use the fundamental theorem of calculus part 2. Here's all we have to do. We need to go to the antiderivative. This was section 4.9. That's a good section to return to see the various formulas that can get involved. The notes that we wrote down also showed some really important formulas, some of which we'll turn to today. One of the formulas was, if you're finding the antiderivative of a function like this one, all we're doing is using the power rule in reverse. We'll put down a 5, then an x, power on x is 1, so it bumps up to a power 2. In the antiderivative, the exponents increase for a power function. Then we divide by that new exponent. Then we could just pause right here. It's a good idea to do a mental check on these as you go step by step. If you were to differentiate just this, ask yourself, what would you get? 2 comes down, cancels that 2 down below, and you really would just get 5x when you differentiate this function in blue. That means it satisfies this property for just the first term, and now we need to move and get the antiderivative of the very next term. Boils down to, what is the antiderivative of a constant? In section 4.9, we just multiply it by x. So if it's a 1, we can just say 1 times x. Better to just say x for short. That tracks because the derivative of x is 1. So that's our full-on antiderivative. We'll take that entire group, 5 halves, x squared plus x, evaluate it from a lower limit of 0 to an upper limit of 2. So we're at this step with the critical notation. We found the antiderivative. We're going to evaluate it. We're essentially going to be doing this on the next step, but we always put in the step in the middle to convey what was the antiderivative to begin with when we organize our results. So now we are ready for the next step. And the process is always the same. Always start with the upper limit of integration. Even if those limits were changed, if we are going from 2 to 0 instead, you have to start with whatever number is there, even if it's the smaller number. So we'll begin with 2. This becomes 5/2. 2 squared plus 2. Go minus and put in a 0. We need parentheses. Maybe not so much this time because we're throwing in a 0. The whole thing is 0. But in general, if that was a 1 instead, because there's 2 terms in this antiderivative, we need a parenthesis so that the negative sign can distribute through. But this one is just 5/2 times 0 squared plus 0. We're putting it down on the notes just to show the pattern for doing the evaluation. If you just said minus 0 or you didn't put anything at all, I'll just assume you did this part in your head. Now all we have to do is simplify this further. This is 5/2 times 4 plus 2. This boils down to 5 times 2 plus 2, and it's absolutely 12. We got it the same exact way in section 5.2. Well, excuse me, we got the same exact answer in section 5.2, but in a really tedious way. We had to break things up, find the area of different components. This is quite a bit faster. So far, this is how the evaluation theorem goes. Ashton says, did the plus C for antiderivatives matter in these questions, or is it okay to leave it out since we'll always be canceled? Thanks for mentioning that. That's one of the things that I didn't mention here. It says f is any antiderivative. So you would be correct, just like you said, if you put in a plus C on any one of these. But because of the subtraction right here, you're also correct. It would always just cancel out. So one comment I just forgot to write down here is, let's see if I can squeeze it in this way. Going by where it says any constant, thanks for asking about that. We use the simplest antiderivative, where the constant of integration C will be set to 0. It can be any number, but if this is f of b plus c minus f of a is a group plus c, the constant is just gone. So it always cancels out, just like you mentioned. That's a great question, a great insight on that one. Other questions at the moment? Okay, let's take a look at a couple more just to see how weird these can all get. This one says integrate from -2 to -1 of 1 over x dx. But this is the one where we have to be really, really careful. The power rule works on 5x, it works on 1. That's really x power 0 hanging out there. But there is one particular exponent where it never, ever works. That's when x has a power of -1, which it will have when you bring it up into the numerator, the base up into the numerator. So when 1 over x ever comes up, let's bring in that formula and cite it in the notes just for reference. We use this idea. For 1 over x, the antiderivative is now the natural log of the absolute value of x. The absolute values are also critical here. Sure, if we're just finding the antiderivative, we throw on a constant. But for us, we'll drop that constant since we're doing a definite integral. And you know, just in the next section, 5.4, it will be the indefinite integrals, and those are the times where we will leave the constant on. So let's throw this into the notes just as a reminder for this important formula. It's easy to forget about, and it's just as easy to forget about the absolute values. So what we did with this problem is we forced in a situation where without the absolute values, we can't get a right answer, just to highlight its importance. So armed with that formula, we can say that this whole thing, the area under the curve from -2 to -1 of 1 over x turns into the natural log of the absolute value of x. Then we take that whole thing and evaluate it from -2 to -1. Absolute values are critical here because natural log of -1 is undefined. But throw absolute values on it, and now it is defined. This is natural log of the absolute value of -1 minus the natural log of the absolute value of -2. So we evaluated the antiderivative in blue from the upper limit to the lower limit with minus in between. This then turns into natural log of 1 minus natural log of 2. Natural log of 1 is exactly 0, so this is altogether negative natural log 2. And that means our work is done. All we needed was the right antiderivative. This one is a very, very tricky one. It goes all the way back to differentiating logarithmic functions in section 3.6, where this function really came from. But once we have it, the rest of it is just following the formalities. Well, although this one is done, one comment that we made last time when we were in section 5.2 is it's easy to kind of lose our way when we're doing this. This looks very abstract on paper. It just looks like some weird symbols that someone made up, and we're just pushing symbols, pressing the I believe button, and somehow this is the right answer, and there are no other right answers. But if we can put a picture in our mind's eye that tells us what that number is really all about, it's really worth that effort, because then this doesn't just become some weird black box that gives you a number. You'll have geometric intuition behind every time you do this kind of problem, which, sometimes that can save the day. You might know when you're expecting a negative or a positive number. Negative natural log 2, roughly negative 0.693, is exactly the area under this curve. Let's plot that. It's the function y equals 1 over x. But we want a specific domain. It's not even continuous on anything that includes 0. So we want to go from -2 less than or equals x less than or equals to -1. And that's the area under this curve here. So it's negative 0.693. It's plausible. That looks about right. It's in the right ballpark. It's definitely negative. It's below the horizontal axis. And now if we were to work on this really, really hard, here's what the picture would look like. So what I've done from here is I put together that same kind of plot. Here's this curve going from -2. It says -2.2, but it really starts off right at -2, all the way to, supposed to go to -1, went a little bit further. So it's supposed to cut off at -1. Might have to debug my code a little bit. Supposed to end at -2. It looks like I let it graph a little bit further. Well, let's suppose we're trying to find the area under this curve, and all we had was these kind of tools. Left endpoint rules, midpoint rules. They get really tedious even at 4, but we hinted you could just make computer technology do it for us. And here's what it looks like if we're using, this is the right endpoint rule with 4 rectangles, 4 subintervals. This is the picture we would look at. My curve kind of got hidden there, so I could make this more fancy, but this was a really fast one that we slapped together before class today. If you find the area of those 4 rectangles, it's negative 0.759. Our work through the fundamental theorem said it should be negative 6.93. So our estimate is an underestimate. We're going way below the curve on these points right here, on these rectangles right here. The only way to improve this estimate is to increase the number of rectangles. We can go from 4 to 16. 16 would be like a really nasty homework problem where it feels like busy work, but in principle, you could do this by hand. And this is what it would look like. We have a more refined sawtooth kind of pattern. If you find the area of all of these rectangles, it's now negative 0.709. Not quite what we want, but it's improving. But if we want to really evaluate this, we have to take the limit as n goes to infinity. So we wouldn't be satisfied at 16. We'd go off to 40 and see what that comes out as. At 40, this is the new picture. It's now negative 6.994. It's improving each time we go at this. We're accurate to 2 digits. We go from 40 to 80. This still isn't the right answer, and we're getting to the limit of how this can even be plotted with the technology we have. Now it's negative 0.696. That 6 should be a 3. So let's see if we can push this further. 160 rectangles. We're really taking the limit as n goes to infinity, so that's appropriate. Here it's kind of hard to really see these anymore as rectangles. Maybe if you squint at this hard enough, you can see them. And it's getting closer and closer to the right answer, negative 0.693 and some change. We put in a ridiculous value, 1600. Then it can't ever plot these rectangles any longer. It just looks like a solid shading for the area. And now it's very, very close. But it's still not quite there. The exact answer is negative 0.6931, and that non-repeating irrational number, natural log 2. So we're still off on this. So that's the power of what we really did. To get the exact area, you really need to take the limit as n goes to infinity on the right endpoint rule. Even this computer system, as impressive as it is, it can't do that limit. This is a finite device, this code right here. So I can't take the limit as n goes to infinity at all on this. So even with the fanciest computer technology available, this fundamental theorem is still extremely amazing. It says you never needed to look at the limit whatsoever. All you needed was the antiderivative, and that's the exact answer. So that puts together pretty much everything we've done from section 5.1, including 4.9, the antiderivative, to show how all of our methods working with derivatives have culminated in finding this exact area under the curve. So every time you integrate, find a definite integral, just think of the area picture to explain why you have a negative number or a positive number, and so on. Well, any questions at all with the weird demonstration here? Okay, well, let's take a look into, I think I have just a couple more to end the notes on. Actually, that looks like it's the last one. We'll end the notes here on this last one, and then just take a preview at the next section, 5.4, indefinite integrals. So this one is kind of a reminder of things that happened in the antiderivative section. We need to be really careful when we take antiderivatives. Antiderivatives are not the most friendly things. We've hinted at that before, and we'll continue to hint at that in the next section notes. But some antiderivatives that absolutely can give us trouble are things that look like, say, maybe not that one. Lost my place here. How about, we didn't do anything quite like that. Interesting. These ones were definitely pretty tricky, but we haven't done one quite like this one, it turns out. That makes this antiderivative kind of new in a certain sense. And the comment I was going to go on about with this one is, you cannot find the antiderivative of this integrand by finding the antiderivative of the first piece times the antiderivative of the second piece. In fact, if you were to differentiate it, that doesn't work the same way either. The derivative of this is not the derivative of the first piece times the derivative of the second piece. You would need the product rule. And we wouldn't even want to use the product rule on that. We would want to expand first for trying to find the derivative. That's a faster way straightforward way to get through it. And same idea with antiderivatives. If you want the antiderivative of that without expanding it, you're essentially doing the product rule in reverse. We do something similar called integration by parts in calculus 2, but this is a totally inappropriate problem for something like that. So if you see something like this, what we must do is expand and simplify first. If something is being divided, divide first as well. Same kind of idea. So before we even get started on this one, let's take a look at 5x plus 1 times x minus 1. If we expand, we get 5x squared minus 5x plus x minus 1. And sometimes people might stop at this stage, throw it back in and integrate. It will work, but simplifying is your friend on these kinds of things. Doing the evaluation, if you have 4 terms, can get really kind of messy on these. Anything you do to simplify this, even if it's as a small step as combining like terms, it's absolutely well worth the effort. So it's always good to go another step further, 5x squared minus 4x. We probably would do that anyways because our training in algebra kind of drilled that into us. But here it's really vital. Take every simplification you can possibly find before you go for the antiderivative. So now it's an integral from 1 to 2 of 5x squared minus 4x minus 1 dx. And now at this stage, it's not that bad. There's no 1 over x or x power negative 1 anywhere inside here whatsoever. So we can now just go term by term and find the antiderivative. So start off by writing 5, then the base x. The power goes up 1 higher than what we see here, so now it's power 3. So we divide by that power 3. We differentiate that, 3 comes down, canceling with the 3 below, and it's just 5x squared. Power would go down when we differentiate, matching this term here. Then it's just rinse and repeat. Antiderivative of this one, well, sometimes we look ahead a little bit first. There's definitely going to be a negative sign, give it some space, put in base x. It's absolutely getting to a power 2, but then whatever's in front gets divided by that power 2. So oftentimes we'll see people do it this way. Jump right to negative 2x squared. So what they visualized is this power becoming a 2. 2 will divide that 4, so just plug in a negative 2. A quick mental check. Always a good idea when you're doing these for the first time, and really any time. It's easy to make mistakes. I mentally check these as I go. Differentiate this. 2 multiplies and it becomes a negative 4x as above. Then antiderivative of negative 1 becomes negative x. And now we have 3 terms. We're taking that entire output, evaluating from 1 to 2. So that's what it looks like so far. Take all this stuff, first evaluate at 2, then evaluate at 1. Take the difference of those results, and we'll know the dead-on exact area under this curve, which is just as complicated as this one, because it's not a triangle or rectangle arguments you can use on these whatsoever. This one's a quadratic. It has some alarming curvature, making area arguments very, very difficult. Any questions with the antiderivative before we go to finalize it? Okay, so here's what the conclusion is going to look like. In place of x, throw in 2. So the whole function becomes 5/3, 2 cubed, minus 2 by 2 squared, minus 2. Then subtraction is always in the middle when we go to the next step. Parenthesis to make this algebraically correct. Plug in the lower limit of 1 into the same exact function. This would be 5/3, really just 5/3, but I'm going to say it this way in the notes. 5/3 times 1 cubed, just to highlight the pattern. You don't have to do that in your own work if you want to simplify just to 5/3 right away. Then along similar lines, negative 2 times 1 squared minus 1. So now it became just a big mess, really. We need to simplify this down, get an exact answer out. So this becomes 5/3 times 8 minus 8 minus 2 minus 5/3. This is negative 2 minus 1, so minus 3. So this becomes 40/3 minus 10 minus 5/3 plus 3. It just becomes a good review of arithmetic, I'd say, at this stage. So now it's 35/3 minus 7, which becomes 35/3 minus 21/3 for least common denominator. So we get exactly, let me double check, 14/3 is what it looks like. So there's our exact answer for the area under this curve. We have a positive number. Doesn't mean the curve is always above the x-axis, but it does convey that in the net area, it's going to have more of the curve above the x-axis than below because we got a positive answer. And potentially, if we plot this, we might see that the whole curve really is above the x-axis. It's just not a guarantee when we see the positive number. But we did it. That's the fundamental of calculus, both parts 1, parts 2. We're going to emphasize in a strong way, section 5.4, this part of the process, finding the antiderivative right there in blue. Because the thing to notice about all of this is, if you're going to use the fundamental theorem of calculus part 2, you have to have that antiderivative in the first place. So we're going to have a segue section 5.4 next, where that's the whole section in a certain sense, getting an antiderivative. And then section 5.4, it's going to show us how to take and do problems like these that are just a little bit more involved. Something where a chain rule had occurred, and we have to reverse the chain rule. That's section 5.5, which we'll call U substitution. So this is where the notes end. We'll take about a 9 to 12-ish minute look at the very next section, just to see how it goes, start off a couple problems. Here's our section 5.4 on the definite integrals. It says definite integrals and the net change theorem, which sounds like something new, but when you really look at that net change theorem, stare at it really closely, this is nothing but the fundamental theorem of calculus part 2. We're just going to use it in a more applied setting, which gives us this fancy name. The integral of a rate of change is the net change. And we'll do an applied problem at the very end here when we come back after our third exam on Tuesday. So first, here is what we mean by indefinite integrals. If we have a function f that's continuous, f, uppercase F will be denoted its antiderivative, which means in our section 4.9, the derivative of f of x is lowercase f of x here. But we'd like to use different notation when we indicate that. Our new notation that we're going to use is the indefinite integral of f of x is the antiderivative, and now we actually use the constant is part of the answer at this point. So when we go to find the indefinite integral, what makes it indefinite is there's no lower limit or upper limit of integration whatsoever here. This means it's just now a fancy symbol for antiderivative. That's literally what that integral sign is meaning. Which also means the constant of integration C is required. So we have to have it as part of our answer. And now this means there are two kinds of integrals that we're looking into. A definite integral versus an indefinite integral. It's a good idea to pay attention to the meaning of both of them. So let's put down here just for a quick reminder on the notes. A definite integral is a number representing net area. Net in the sense that it's taking the signed area, positive area, totaling with the negative area over that domain, and kind of net in the same sense of the net change theorem. So we call that net area. It's written this way. Definite integral means you're integrating from a to b, f of x, dx. So that's how we spot our definite integrals. And the answer is just a number. But if you go to an indefinite integral, and indefinite integral is an entire, let's say, an infinite family of functions indexed by the constant c. So when we go to solve an indefinite integral, we're getting an actual function, something that varies with x. It's a family of functions, an infinite one, because every new choice of the real number c here gives you a different function. They'll all have the same exact derivative, but this gives us just a different family of functions where that curve, whatever it is, can go up or down vertically, depending on the constant c. So a definite integral is nothing but a number, but an indefinite integral is a function, or a family of functions is the most correct way to say it. So that's the difference between the integrals. Essentially, what that means then is section 5.4 is nothing but section 4.9 in disguise. All we're really doing is using a new notation, the integral sign itself. Our author in this section 5.4 has a selection of important indefinite integrals and properties of integration. If you find the indefinite integral, the antiderivative of c times f of x, you get c times the indefinite integral of f of x, or antiderivative of f of x. Oftentimes we'll say this in a kind of a faster way. We'll just often say the integral of c times f of x is c times the integral of f of x, where knowing if it's a definite integral versus an indefinite integral is in context by whether or not there's limits of integration. So again, we often just say the integral of, meaning either antiderivative or assigned area. There are more properties. Here's the sum rule, integral of a constant. This is our wonderful power rule going in reverse, and this is the exception. Notice the inclusion of the absolute values on the natural log x. A lot of other properties. These are really just properties of derivatives, stated now as antiderivatives. The antiderivative of an exponential is itself, but because we're forming an antiderivative, we throw on the constant. If it's any other exponential not to base e, we divide by the natural log a, then add the constant. This is essentially our trig table, but we're taking antiderivatives of things we saw on the right. Antiderivative of sine is negative cosine. Secant squared is tangent. That's because the derivative of tangent is secant squared. Includes some inverse things, inverse functions, and some hyperbolics. So it's absolutely not a complete list, but it's a good list to just put down a short, nice table. So I would say if you're putting together a table, maybe it's say for the sake of the final exam, for antiderivatives, what I would do instead is don't rely on this as the end table that you would use. Instead, go hunting and dig up, say, stuff from section 3.3. You want a table that uses all of this. So I would take this, readapt it this way, by just putting an integral sign and say, in other words, the integral of cosine x dx is sine x, and so on and so forth. I think just about everything is here for this one table. But if you go to the inverses, say section 3.6, there's definitely stuff missing on this one. Go to this table as well. Here it is. There's really two sets of formulas here altogether. If you have this table down, say for your notes on the final exam, that's really pretty good because you don't necessarily need to write an antiderivative on every one of these formulas. Just remind yourself that if that came up right there with the red dot, then it just means the antiderivative of 1 over x. You know, I forgot my constant up here on sine. Don't forget the constants. Those are important. Let's make sure we include those there, even if we're stating a simple antiderivative formula. On this one, you could just remind yourself that if you have x times root x squared minus 1 dx, this is nothing but secant inverse x plus the constant. So again, you don't need to double up your table. Just remind yourself that it goes forwards when you differentiate and backwards when you find the antiderivative. So definitely keep these tables in mind because this list, although nice in the textbook, isn't the end-all be-all. We covered more than just the set of derivatives slash antiderivatives. So these are always great tables to come back to. And let's maybe do one problem so we don't get too far ahead. That's a good one to come back to after we're done with the exam on Monday. If you take it on that day, like the others, you're welcome to schedule through Thursday. We'll come back on Tuesday, review antiderivatives, getting through this next one down below. So this is our next one to get through. And maybe it's a good reminder that another table you'd want to go to is section 3.11. Look at all your derivatives of the hyperbolics. And they are double duty as antiderivatives for the hyperbolics. So to solve this one, here's the function we want the antiderivative for. The answer is going to be a true antiderivative. And the antiderivative of hyperbolic sine, let's scroll up a little bit, is going to be hyperbolic cosine. The hyperbolics are kind of nice for sine and cosine versions because when you differentiate hyperbolic cosine or hyperbolic sine, those negatives never come up. Those negatives are problematic if it's an ordinary sine and cosine. You have to be very, very careful with those. So down here, we said that the antiderivative goes like this, minus cosine x. I'm going to delete that in a moment. We're in trouble right here because our check is always differentiate whatever your answer is. We still need to put the constant. But the issue is derivative of hyperbolic cosine is hyperbolic sine, so that's okay. The derivative of cosine is negative sine, which cancels with that negative sign, which would give you positive sign. We didn't land on the right constant. So the antiderivative here is not go minus and then cosine x. If sine x comes up, and we want an antiderivative of that one, well, here's what the table looks like. If you have a negative sine x, it goes to cosine x altogether. So this becomes plus cosine x. But really, I'd say the best protection here, let me throw in the constant before I totally forget again. The best protection whenever you do this problem, no matter what is, just differentiate your answer. That was what chapter 3 was all about. We spent the most time in this course in chapter 3, I believe. So if you do a check on the margin, it's always well worth it. If you have extra time in an exam setting, for example, it's worth the effort. Derivative here is hyperbolic sine. Derivative of cosine is negative sine. And so we're on the right track. And that's all we have to do. If there is no limits of integration, we must include the constant c, and we're not trying to get the area like up here. We just end the answer on the antiderivative. But we'll do many more when we come back on Tuesday's class of next week. But I don't want to go right to the very end minute. I think this next one takes a decent amount of time on the algebra side, just on its own. That's a good one to refresh on. So any last questions or comments before we call it a day today? Okay, well, thanks to your hard work and to everyone else that sees this video later on. Like I mentioned before, all the other exams, good idea to be prepared is make sure you're completely caught up on all those homework sets. I'll be checking the homework very carefully on Friday, Saturday, Sunday. I typically grade in the morning. So even if you send me something, say, at 1 a.m. on Monday night, I'll be grading homework first thing on Monday to get your feedback as soon as possible. I'll try to include detailed feedback. So get caught up on the homework sets. Try to get your page of notes done early, since that's a great step. That just helps you study, helps you with your homework sets on its own. And take a look at the extra sample problems or the blank lecture notes at the top for extra practice. But have a great weekend. Try not to work too hard, and we'll be back to this on Tuesday. Take care.